So in this example here, it says it reads a current IT, that's 5 sine 100t flows through the inductor. So this is the inductor in Henry, right? And there's a sinusoidal current, right? Okay, so what is the voltage uh, across the inductor at 5 seconds, right? So that's what it's asking us to do. So clearly what this says is that because this is sinusoidal, we can't use V is equal to IR, which is when we use the indirect current, right? But rather what we, especially here, where here is the case that we have an inductor, the equation that we use here is that we have let's see, V, which is sinusoidal, right? Sinusoidal voltage that we're looking for, and then is equal to the inductance, and we have the I, right, the T, right? So that's what we need to do, right? So let's see. So we have the current, right? So that what this whole thing says is that we are trying to find the voltage, right? If we are trying to find this sinusoidal voltage, it will be the inductance, right, which we have, and then this the IDT, right? So that's the I, the T, and then we have this. That means I will have to take the derivative of the current, right? The T, and the current that we have here is 5 sine, right? So that's so we have 5 sine, right? To bracket, let's make this 100 T. Right? So this is what we need to do to actually find this, right? So we know that the LS was 0.2, which was 0.2 Henry, that was given directly, right? And then the IDT is basically mean that we have to find the derivative of that. But if you have to do it step by step manually, you have to show all this. So basically we end up getting 5, right? And we're getting, if we find the derivative, right? So we end up getting let's see, you get 5 times 100, right? So that's you find the derivative, and then we have cos bracket 100, right, t. So that's what we have, right? So that will mean that that's 0.2, right, times 5. Let's move this so everything will fit, right? That's if you are doing the manual, and that's specify that we are finding it at t is equal to 5, right? So that's at t is equal to 5 seconds, right? So that's 0.5 times 100 cos, right, into bracket 100 times 5, right? So this is what will give us an answer. But remember, it's very important that because we have this trig here, what we do is that when you are doing the calculation, you do it in radians, right? We do it in radians. And we've already said that if it's something that you have to choose from a number of options, there's a way to actually punch everything directly to give you the final answer you're looking for. We are going to test both uh, both ways of doing it to see the answer that we get, right? So let's see. Let's set derivative something, right? All right. So yeah, we're going to punch the one that we've done manually first, and then we point the derivative directly and see what we get with that. We are supposed to get the same thing. So far as we do everything in radians, right? So let's see. I'm changing it to radians. So here, so degrees now is in radians, right? So let's see. We are going to compare both answers. So let's see. I'm going to show both. So the first one here, this one we did it manually. That's 0.2 times 5 times 100, right? Sorry, 100 cos, right? 100 times 5, right? Yeah. So we check both, and when we try to do it uh, directly, right? So that would be 0.2, right? And then we punch in the derivative. So that's how we go about it, right? And we put in the original function, which is this one right here, right? The original current function, which is this, right? So that's 5 sine 100, and we are representing the t here with x, right? So x, okay, and we are taking it when the time is 5, right? So 5. So let's see what we get for both. So the first one, which is this, the one with the manual, gives us a current of, so the minus is just opposite direction, right? So that's what you're saying. That's 88.3849 amperes, right? And then for the Yeah, so see the same thing when we punch it. So that's still 88.3849 approximately. Yeah, right. So that's what we are getting. So for this particular one, the current across it is this. Right. So if it to be in a circuit, the minus is just specifying that it's in the opposite direction to what is initially given. Right. Line error. So because this is voltage, right? Yeah, voltage across the inductor. This should be V. Yeah, this should be V. So now we will try another example. Right. So this one here says that the voltage across 0.5, sorry, the voltage across a 50 millihenry, right, inductor is this, and then the initial current is 0. We are supposed to find the current at 10 seconds, right? So this is what it means. So this one again, we use the same equation, right? What we have, we're supposed to find the current, right? The current, and here, yeah, so we're trying to find the current. So let's see. The equation itself is V, small current T, is equal to L, and we have the I dt, right? Okay, so let's see. So if you are finding the current, that will mean that we have to do some integrations, right? So that will mean that if we are trying to find current, we first of all have to make the t, the I dt the subject, right? Be equal to this vt here, right? All on L, right? Okay, so this is what we do. Okay, the vt that we're having here is the, what's the name? The 20, right? Cos 200. Let's try this one. Cos 200, and then we have T, right? And then the L, or the inductance that we have here is 50 millihenry, right? So that's 50. The milli is 10 to the power minus 3, right? Yeah. So this is the I, the T. So that means that if we want to really find I, then we have to do integration, right? Integration. So the I, which is a function of time, is basically the integral of this, right? Yeah. So that's of all that we have there. And when we simplify all this, what we end up getting is, so let's punch there. So that's 20 on 50 times 10 to the power minus 3, right? Yeah, so we have 400 cos 200 t, right? So this way we are doing. Okay, now for us to find the current. So when we integrate this, what we get is 2. Then again, it depends whether actually step by step or 2. If it's you have to choose from options, you can actually do this integration directly, right? So let's see. When we do it directly, right? So 400 400 when we do this directly, we get, let's see, 2, right, sine bracket 200 t plus a constant, right? So this is the I as a function of time. But then clearly it says that the initial current, so at time, is equal to 0, right? It says that the initial current is 0. So that would mean that when time is 0, right? When time is 0, when t is 0, that's in the initial current is 0, right? So that would mean that at that point, that's 0 is equal to 2 sine 0 plus c, right? And if it's so, that will clearly imply that c is equal to 0, right? C is equal to 0. Let's see, 2 sine 0, right? So this is 0. That will mean that c is equal to 0, right? So if c is equal to 0, that will mean that the current at the 5, right? It says we should find it at, what's the name, 10 seconds. So current at 10 is equal to 2 sine, right? Let's make this one. Right. That's 2 sine 200, right? And we know the time that we are looking for. We said at 10, right? So 10. So this will get. So that's 2 sine 200 times 10. So this will get. So that will mean that the current at the 10 seconds is basically 1.860 at 40p 1 amperes. The unit is very important, amperes. So for such a problem like this is what we get. All right.